Hello, and welcome to this virtual roundtable brought to you by Smart Water Magazine. I'm Cristina Novo, Technical Editor at Smart Water Magazine, and I'm delighted to have you with us today. We're going to explore a key priority for the future of desalination, improving energy efficiency through innovation to support long-term sustainability. Desalination has become an essential solution for addressing water scarcity and ensuring a reliable supply in water-stressed regions. However, rising energy costs and growing sustainability demands make improving efficiency more important than ever. Every kilowatt saved translates into cost reductions, a smaller carbon footprint, and more sustainable water production. In today's webinar, we're going to explore a range of topics that are critical to the future of energy-efficient desalination. We'll start with an exploration of the current state of desalination and global trends, highlighting technological advancements and sustainability practices that are shaping the sector. Next, we'll dive into energy optimization strategies for large-scale desalination projects, discussing how innovative approaches can significantly reduce energy consumption. We will also tackle the crucial topic of brine management and resource recovery, looking at sustainable methods that turn byproducts into valuable resources, improving both environmental and economic outcomes. Finally, we'll examine the role of high-efficiency motor solutions and how they contribute to optimizing energy use across desalination processes. These topics will be presented by a distinguished panel of industry experts. Following their presentations, we'll have a Q&A session, giving you the opportunity to engage directly with the speakers and explore the implications of today's topics. But before we get into the main content, a few quick notes. We encourage you to submit questions at any time during the webinar using the Q&A module that you will find at the bottom of your Zoom screen. To ask a question, please include your name and organization. By attending today's session, you're eligible to earn a continuing professional development credit. And to receive a certificate of attendance, you would need to scan the QR code that will be displayed on the screen. Also, if you would like to follow the webinar in a different language, you can select your preferred language for subtitles at the bottom of the Zoom screen. And now let's meet our speakers. We're privileged to have with us today 4 experts who bring a wealth of experience and knowledge in energy efficiency for desalination. First, we welcome Domingo Zarzo. He is the president of AEDIR, the Spanish Desalination and Reuse Association, and he is Innovation and Strategic Projects Manager at Sathir Water. Domingo brings over 35 years of experience in the water sector, having led major projects across the globe. A frequent speaker at global forums, including COP25, COP28, and the UN Water Conference in New York, he has also contributed to academia as an associate professor and currently honorary collaborator at the University of Alicante in Spain. Today, he will provide an overview of the current state of desalination, discussing global trends and technological advancements. Next, we will listen to Miguel Aritio, Director of Energy Resources and Business Development for North Africa at Acciona. With extensive experience in both renewable energy and water treatment, Miguel has spent the past decade developing water treatment projects worldwide. Currently, he also focuses on integrating renewable energy into Acciona's water treatment operations. Today, he will share strategies for optimizing energy use in desalination, including the integration of renewable sources of energy. Our third speaker is Christos Harisiadis, Solution Architect in Water Innovation and founder of Brine Consulting. With over 8 years of experience in desalination, brine management, and industrial water reuse, he specializes in integrating engineering, business strategy, and sustainability to develop commercially viable water solutions that are also future-proof. He has worked on high-profile projects like NEOM and large-scale industrial water infrastructure. Christos will share innovative approaches to turning desalination byproducts into valuable resources. And our fourth expert is Jesus Rivas, Water and Wastewater Global Manager at WEG. With over 25 years of experience in water treatment, desalination, and industrial water management, Jesus has held leadership roles in international companies, overseeing business development, engineering, and project execution across various world regions. At WEG, he leads global initiatives to drive innovation and sustainable solutions in the sector. Today, he will discuss how high-efficiency motors can optimize energy consumption in desalination operations. So let's get started. I'm delighted to hand the floor over to our first speaker, Domingo Zarzo.
Thank you. Good afternoon, Cristina. Thank you, Cristina and Smart Water Magazine for organizing this and for inviting me to participate. Now I will be sharing the presentation. Okay. Today I will be speaking about the global overview of desalination, the current state of global trends in desalination. Maybe some things that I will be saying will be obvious for many of you, but I would like to introduce the subject with this introductory presentation. This is the menu for today with different things I will be speaking about. First of all, for speaking about the global water crisis, you know that 800 million people lack of drinking water supply and 2.2 billion don't have a safe supply. 3.6 billion of people have no sanitation systems, and 70% of the water in the world is used for agriculture, with estimations about, from United Nations to double this food production by 2050. That means that we will have more needs of new sources of water. And why desalination? Is obvious. 97.5% of water in the planet is in the ocean. With the effects of climate change and pollution, availability of conventional water sources are reduced, of course. This is the global overview of desalination. We have in the world something like 20,000 desalination plants all over the world, producing approximately 100 cubic hectometers per day. Approximately 60% of those plants are producing fresh water from seawater. And there are evidently other sources like groundwater, superficial water, or even wastewater. 65% is produced by RO, by reverse osmosis, by membranes, with a very fast increase of the technology of reverse osmosis, because evaporation technologies have a very high energy consumption. And Spain is the 5th country in installed capacity, with a rarity in front of other countries, that more than 21% of our desalinated water is going for agriculture, which is something special in our country. There are many countries with desalination programs. The largest desal programs and countries are Saudi Arabia, Emirates, or the United States. And speaking about the Spanish industry, 7 of the largest 20 desal companies in the world are Spanish, demonstrating the strength of our industry, which is including not only large companies, also small and medium, consultant companies, research and development centers, universities, etc. First, before to speak about the energy consumption of desalination, I would like to dismantle some myths about desalination that are it seems that even in mass media, they are using those. There are 3 typical mantras about the desalination. Desalination is energy intensive. Desalination has a strong impact in marine environment. And desalinated water is very expensive. For example, agriculture can't afford desalinated water. And I want to demonstrate that this is not true with facts. Currently, the average energy consumption in desalination is something like 3 kilowatts hour per cubic meter, which means 0.003 kilowatts hour per liter. If we consider by liter, you can see the difference. For example, the energy for producing the desalinated water for a family of 4 members during a year is the same consumption that the refrigerator. Or, for example, doing one click in Google searching for something is consuming the same energy that to produce a glass of water. Those kind of comparisons are clear. Speaking about the impact in marine environment, some methods from the discharge point, brine is simply seawater again with any kind of impact. And maybe you can see, if I'm saying this, it seems that, of course, I'm defending desalination, but this is demonstrated by science and the academia. It's not, they are not my words. And speaking about the cost of desalination, compared with, because you can see the price per liter, which is reduced, and you compare with bottled water, for example, is 500 times more expensive. And we can see, you can see in the webpage of the producers of bottled water that the energy consumption is 30 kilowatts hour per cubic meter, which means it's very high. In our case, in IDIR, the Spanish Desalination and Reuse Association, where I'm the president, we published last year a communication campaign called 10 Certainties about Desalination, trying to dismantle all these kinds of myths with facts, data, and with science and contribution from the academia. Now we are preparing something similar for reuse. Speaking about the energy consumption in desalination, of course, you have different sources of energy consumption, the intake, the pretreatment, the RO, which includes the high pressure pumps, the RO trains, and the energy recovery devices, of course, is the main point of energy consumption, maybe the 60% or 70%, depending on the plant. You have also the post-treatment, ancillary equipment, and product water distribution. In some cases, for example, in mining desal plants in Chile, for example, with important pumping stations, sometimes even the pumping energy consumption is even higher than the desalination itself. No? There are different cases. Of course, it is also depending on technology. If evaporation has a very high consumption, more than membranes, the salinity of the raw water, the distances between intake, plant, and distribution, and energy represents 50-60% of the water production cost, which means that it's very important for reducing the cost of desalinated water. Speaking about the energy consumption over time, this is a graph made with data with the Spanish desal plants from the first plant which was built in 1964 in Canary Island. It was an evaporation plant, and you can see that in the 70s, we were speaking about 25 kilowatts hour per cubic meter, 25 or 30. With the time, we were changing the technology. First, more efficient evaporation technologies like a vapor compression, etc. But in the 80s, with the spreading of our membranes, the energy consumption was more reduced. Of course, an RO plant treating seawater without any kind of energy recovery could be a consumption around 8 kilowatts hour per cubic meter, but with the implementation of the energy recovery devices, which are taking advantage of the pressure at the high volume of the brine, you can reduce more. And we have seen also an evolution in those kind of energy recovery devices from the first turbines, Pelton turbines, until the new pressure isobaric exchangers from different manufacturers. And currently, we can speak about 2.53 kilowatts hour per cubic meter. And it seems that you can think that we could reduce much more with different technologies or other devices, but this is not possible. We have a small problem called thermodynamics laws, which and due to this reason, it's impossible to produce desalinated water from seawater with less than approximately 1 kilowatt hour per cubic meter. That means that we have a better reduced space or room for reducing more. But I would like to remark that desalination is the only industry which has reduced the energy consumption by 10 in the last 50 years. Speaking about current typical measures for energy consumption reduction, you have different membranes with new materials, more productivity, the use of hybrid systems, splits, etc. The arrow configurations, for example, the pressure centers or concentrated less pumps feeding different trains, if you like it. This is a design criteria, or variable frequency drives, booster pumps, etc. Of course, the pretreatment has impact over the energy consumption, the kind of energy recovery devices, the efficiency and the efficient equipment in motors, pumps. We will be speaking about it after. The optimization by new technologies like artificial intelligence with optimizing the energy consumption in different points. And also you can produce energy from brines with turbines or energy production for different. And can we expect a significant additional reduction in energy consumption? As I said before, no. Thermodynamic limit is around 1 kilowatt hour per cubic meter, which means that we are very close to this point. Of course, another stage in where the industry is involved is in the decarbonization, the reduction of our CO2 footprint with the use of renewables. But this has some difficulties for this implementation. One is the production capacity. The energy needed for a large desal plant is high in the points where we are implementing the plant. Of course, a desal plant should be producing continuously as much as possible. And renewables are discontinuous in general, which means storage and more price. The footprint, the available space, in general, our desal plants are in the coast where there are not much space for implementing solar panels or whatever. And sometimes best place for a desal plant is not always the best place for the location of the renewable energy production. For the reasons, some governments such as the Spanish, Australian, and others are buying energy from renewable sources, but not directly coupled with the plants. And for example, the Spanish government has a current decarbonization program for desalination with an important investment for coupling those plants with renewables. You can see here the impact of energy consumption and the reduction. You can see the CAPEX and OPEX for lattice seawater arrow plants from the beginning of the century and recently, and you can see different things. Of course, it depends on the kind of contract, if they are PPP contracts or EPC. It depends on the country. For example, in countries like Australia, the staff cost is very high. For example, in countries in the Middle East, the cost of energy is more reduced. And as you can see, we have been from the $1 US dollar cubic meter at the beginning of the century to almost 0.5 US cubic meter. Of course, in the last plants we are mentioning, we are speaking about huge plants. That means that the scale of economy is clear, but also because there is a difference in that in the Middle East countries, in general, the energy is cheaper. No. Anyway, for me, there are very reduced prices. We will see the economic feasibility of those plants when they will be operating. Speaking about sustainability, in general, all our companies are doing research in desalination, but more focused on sustainability and for reducing impacts than in developing new processes. For example, we are working on, of course, decarbonization of renewables, circular economy, for example, recycling membranes or different components. Brine mining, we will be our colleague Christo will be speaking after the presentation. Energy production from brines, of course, the digital transformation for increasing efficiency, the reduction of impacts, environmental, economical, and social, and of course, the water footprint and social footprint. Another important challenge for desalination for me, as the president of the Spanish Association, is the most important challenge for desalination currently, is to change the social perception and the mass media negative perception about desalination and what they are publishing sometimes without knowledge or without applying technical and scientific knowledge. For example, say the typical thing, I was speaking about those things. It's very expensive, it's very energy intensive, or things like you are poisoning the ocean. You know what I mean? Of course, we have heard about emerging technologies for years, such as forward osmosis, evaporation, membrane distillation, capacity desalination, graphene, or others. But of course, due to the thermodynamic limit of energy consumption, we can expect big advances in energy consumption from them. Only small steps or hybrid processes or others such as brine mining. But the hope in many years ago that one of those technologies could replace reverse osmosis will not happen in a short time. Speaking about the energy production from brines, it's a very interesting thing in order to take advantage of salinity gradient between brine and a source of fresh water by different technologies, and you can use forward osmosis or reverse electrolysis, reducing the overall energy consumption of the plants. And speaking about a new economic and social innovation in the promotion of desalination and reuse, this is the Water Positive Initiative. The Water Positive Initiative is we have a think tank with a group of 400 professionals from all over the world working in development of a technical, legal, and economic framework for the compensation of water footprint, copying or inspiring in the CO2 market for compensating the CO2 footprint. And this is a very interesting initiative. For example, in Spain, there are initiatives from large companies like Microsoft or Amazon that they are compensating their water footprint because they have a very high water consumption due to the refrigeration of the data centers. And you can see here this initiative, and you have our webpage, LinkedIn group, etc. And as conclusions, with recurrent droughts and the effects of climate change, non-conventional water sources have become essential to meet current and future water needs. The activity of desalination is environmentally sustainable when done correctly, which is most of the cases, and it has no relevant effects on the environment and marine species. Current trends in innovation are not focused on developing new technologies, but on increasing sustainability. The desalination sector is involved in a decarbonization process, although if we analyze the problem with perspective, desalination is not so energy intensive as you think. And one of the greatest current challenges of desalination is communication and to face the non-science-based or politicized opinions with scientific knowledge. Thank you very much. I think it was more or less in time. Thank you.
Thank you. Thank you, Domingo Zarzo, President of AEDIR and Innovation and Strategic Projects Manager at Clearwater, for this excellent overview, setting straight the facts about desalination and also getting everybody to speed on the current trends. And we have heard how research and development in desalination is currently focusing on increasing sustainability through decarbonization and renewables, through circular economy and brine mining. And we're going to be hearing a bit more about these aspects in the following presentations. And Domingo has also pointed out a crucial challenge, changing negative perceptions about desalination. We're now going to turn to our next speaker, Miguel Aritio, who will discuss energy optimization strategies in large-scale desalination projects.
Thank you, Cristina. And thank you, Smart, for inviting me to this roundtable. I'm sharing my screen. I'm not sure. Okay. I hope you can see it. Not yet.
Now, yes.
Okay, great. So, well, as I said, thank you very much, Cristina. Thank you very much, Smart Water, to invite me to this roundtable. Well, I guess this is today is one of the main discussion, the main point, the main issues about how to deal with desalination, how to deal with consumption, how to deal with at least at the end the price of the cubic meter when we produce water through non-conventional as the desalination is, right? So I'm pretty sure that my colleagues on the table will be will give much more details about how things works, how efficiency, how the trend, how the market is going, how membranes are improving, how pumps are improving. What I would like to focus in a quickly overview is on how do we treat the situation as a global, and how do we treat the whole thing together, which is desalination in one side, or water treatment in one side, and source of energy in the other one, right? So that, for me, that makes just one project with two different facilities or two different utilities that they might work together. So just I will use this map to show the coast, right? Not where Acciona is, which is in a lot of countries, you can see it, but how long is the coast we have all around the world, in everywhere, and using this coast in most of the places, the coasts are not full of buildings and people are empty, but we can use it for desalination plant, and also at the same time we can use it for feed these desalination plants with renewable energies as the wind or solar. All the water sector is shown in this picture, from intake to pumping stations to treatments, services, drinking the water, using the water, factories, and users, and then treat the sewage water to clean it and send it back to the nature. All these are high consumption energy consumption systems. So we need to see how can we deal with this energy consumption, which I agree with the previous colleague, that is high consumption, but there is is not that expensive. So you see the figures that he showed us, where he compared the refrigerator with the consumption of a family of for desalination water, or the use of the click of in Google to search, that is the same consumption that a glass of water can have. So in any case, we need to reduce the consumption of energy in the water treatment plants. So as I told you, there are several possibilities to do this. All the companies are studying it, different solutions, treating the sewage from at the end, improving efficiency in the motors. Well, there are a lot of ways to improve the consumptions, but I will jump quickly to, as I said at the beginning, the holistic way of treating this problem, which is making both solutions at the same time. So when we talk about a desalination plant, we are talking about almost 40% of the cost of the cubic meter of the water is the energy that is used for treating the water, right? So we need to see how can we deal with that. And today, the competitiveness of the renewable sources are clear. We are talking about prices in kilowatt hours that are much lower than the prices of any other source of energy, carbon, nuclear, whatever is the source. And we have a bunch of different sources that we can choose to supply the facilities, the water treatment facilities. What do we have in the water treatment facilities? We have high consumptions, we talk about it, a flat line, which is not exactly what we have in renewable normally, and we need usually to fit in high voltage the pumps and the motors. On the other hand, what do we have in the renewables? Usually low voltage generation, which is against the way we consume it, so we need to transform. Low energy density, this is how the renewable works, and we have discontinuous generation depending on this. And the sun is clear, during the night we don't have, and with the wind is variable, so we need to treat that to make sure that we can fit the facilities as the way they need it. In this case, I just wanted to make an example of one of the facilities we constructed and we finished just 6 months a year ago, which is Uval 3B. This is a 500,000 cubic meters per day desalination plant, and we install almost 60 megawatt peak of photovoltaics in the surroundings, connected directly to the transformers in the diesel plant. This is theoretically and in reality, this is the maximum that we can have, because in the best days, in the best hours, the photovoltaic is giving you almost 95 to 100% of the consumption of the plant, which is we cannot go above that unless the utility buy the rest of the energy. So in this case, the 60 megawatts, 505,000 cubic meters per day. This was around 20% of the total of the energy consumption during a year. It was fed by these photovoltaics. Which is the situation? In this case, no problem, because there was a lot of space to install the PV, but we need almost in between 3 to 5 times the space of a desalination facility to install the PV plant. So if the desalination facility was 1 hectare of buildings and things, in this case the PV was 4 hectares that we need to use. You can see the density, the way they are installed are east-west, which is a little different, but it works quite well. I'm sure that I can give you some more details in the question and answers. As I advanced this presentation, this is the same plant, Jubail 3B, onshore feed. And as I said, maximum of 20% per year, but a real intensive use of land, which in this case was not the problem because they have land, they have a lot of land, but we were almost using 5 hectares of PV to achieve this 20%. In this case, it's an onshore connected directly to the desalination, which is a very interesting way of doing it, but there are also offshore through PPAs in which you can have the generation wherever you want, and you just have to sign a contract, and using the national grid, which are almost all over the world, you can balance. What will be the best way of doing this? A net balance. Whatever you inject into the grid through the renewable energy, you can use it not at the same time, but you can use it in the diesel facility. Okay, and as you can see, not only efficient, cheaper, and with all the benefits that the renewable are bringing, and the water, of course, but are also very beautiful installation that you can see it like this one, where you find at the on your left the storage tanks of almost 1 million cubic meters and all the PV plant. So that was all. Thank you very much.
Thank you. Thank you, Miguel Aritio, Director of Energy Resources and Business Development for North Africa at Acciona. Miguel has pointed out the big proportion that energy is in making up the total costs of desalination, so up to 40% of the cost per cubic meter of water in a desalination plant. And has outlined renewable supply options, taking advantage of renewable energies with prices that are highly competitive nowadays. And thank you for showing us those images and giving us all those details about the Jubail 3B plant, where you've noted that that very important issue, which is when we're talking about photovoltaic, the issue of land surface that would be needed to be able to have all those solar panels. As we move forward, it is clear that optimizing energy generation as well as consumption is going to be key to making desalination more cost-effective and sustainable. We're now going to hear from our next speaker, who is Christos Harisiadis. He's going to explore innovative approaches to brine management and resource recovery in desalination. I think, Christos, I think we cannot hear you well. Did you touch your microphone? We still cannot hear you, Christos. No, it doesn't seem. Could you try again? Okay, it's unmuted.
Can
There.
you hear me now?
Perfect. Thank you very much.
Okay.
Go ahead.
So today, as Christina mentioned, I am gonna have a presentation about the role of brine management in energy efficiency. Yeah. But first, I would like to do a short presentation of brine consulting. It's an initiative that I started not so long ago when I saw a gap between technical water solutions and real world implementation, too often going wrong. And this is why projects need a commercially viable and profitable approach. And my goal is to exactly bridge that gap. Now, for today, desalination is a necessary technology for water security, but it also comes with a lot of challenges. And today we will explore how we can optimize energy use in brine management, reduce environmental impact, and even turn brine into a resource rather than a waste product. Desalination has become a critical tool in securing freshwater supplies, with almost 96 million cubic meters of water produced on a daily basis. However, for every cubic meter of fresh water, desalination produces 1.5 cubic meters of brine, a concentrated byproduct that, if left untreated, it can cause serious environmental issues. But desalination brine is only part of the story. Industrial activities such as mining, oil and gas extraction, and chemical production also generate massive volumes of high salinity wastewater. While desalination alone is responsible for producing over 142 million cubic meters of brine daily, when combined with industrial wastewater, the global figure is significantly higher. Brine is not only an environmental challenge, it is also an energy burden. Desalination already consumes 0.5% of the world's total electricity production. And if we were to process all the brine using conventional methods, we would need 30% of the world's total energy. Clearly, a more sustainable and energy-efficient approach to brine management is required. Traditional brine treatment relies on thermal evaporation, an energy-intensive process consuming 15 to 20 kilowatt hours per cubic meter for evaporators, 60 to 90 for crystallizers. In contrast, membrane-based technologies provide a more efficient alternative, at least for the evaporators, reducing energy consumption while concentrating brine more effectively. Reverse osmosis, gives us a brine of 7 to 75 grams per liter, and we cannot proceed over that limit due to osmotic pressure limitations. To push the boundaries further, osmotically assisted reverse osmosis, ultra-high pressure RO, electrodialysis, and membrane distillation, just to name a few, membrane concentrators are being used to maximize water recovery while minimizing energy costs. These advanced membranes allow desalination plants to reduce brine volumes significantly and lower operational expenses, making them an essential part of next-generation brine management. No single technology can solve the brine challenge alone. That's why desalination plants are adopting hybrid configurations, which combine multiple processes for higher efficiency and lower energy use. For instance, by integrating reverse osmosis with OARO and crystallization, plants can achieve higher brine concentrations while cutting energy costs. Meanwhile, membrane distillation and resource recovery allow for the extraction of valuable minerals like magnesium or bromine, further improving economic feasibility. These hybrid solutions are already being adopted, showing higher efficiency, lower operational costs, and reduced environmental impact. As brine disposal regulations become stricter, these configurations will be essential for sustainable desalination. As desalination evolves, so does brine management. The future is being shaped by artificial intelligence, digital twin technology, and renewable energy integration, as already mentioned. AI-driven process optimization can cut energy costs up to 20%, predict membrane fouling, and optimize brine concentration strategies in real time. Digital twins, virtual models of desalination plants are helping operators fine-tune performance, reducing waste and energy consumption before real-world changes are made. Meanwhile, renewable energy sources like solar-powered membrane distillation and wind-powered brine concentration are helping desalination plants become less dependent on fossil fuels, making brine treatments even more sustainable. Now, optimizing energy use in brine concentration is the first step, but what if brine could become an asset instead of a liability? Brine valorization transforms waste into a source of high-value minerals, such as magnesium, bromine, and lithium. By incorporating mineral extraction into brine treatment, desalination plants and wastewater treatment can reduce waste volumes while generating revenue, offsetting some of the energy costs of brine treatments. This approach isn't just theoretical, it's already being implemented, proving that desalination can move beyond just that of water production and into resource recovery. Magnesium is one of the most strategically important metals in the world today. As a lightweight, high-strength material, it is critical for industries such as aerospace, automotive manufacturing, and electric vehicles. With increasing global demand, traditional magnesium production methods, such as mining, are environmentally damaging and geopolitically constrained. Brine recovery presents a cleaner, more sustainable alternative, allowing desalination plants to supply magnesium for key industries while reducing waste disposal challenges. Large-scale projects in Saudi Arabia and China have already demonstrated that magnesium recovery from brine is both technically feasible and commercially viable, offering desalination plants a way to turn a costly byproduct into a profitable resource. Now, Bromine is a high-value element used in pharmaceuticals, flame retardants, and water treatment chemicals. Its demand continues to rise, fueled by stricter fire safety regulations and expanding chemical industries. Today, the Dead Sea supplies nearly 85% of global bromine production, proving the commercial potential of bromine extraction from high salinity waters. Yet, desalination brine also contains significant bromine concentrations, making it an untapped opportunity for recovery. By incorporating bromine recovery in desalination processes, plants can reduce disposal costs, create additional revenue streams, and contribute to global supply chains, making desalination not just about water, but about sustainable resource generation. Now, technology alone isn't going to be enough. Policy and industry collaboration are key to scaling sustainable brine management. Governments are setting stricter brine discharge regulations, incentivizing desalination plants to adopt energy-efficient brine treatments. Programs like the Saudi Vision of 2030 and the EU Water Framework Directive are leading the way, while public-private partnerships are funding brine research and innovation. By aligning policy, research, and industry efforts, desalination can evolve into a fully sustainable and resource-efficient sector. Now, conclusion and final thoughts. Brine management is no longer just an environmental challenge. It is an opportunity for innovation and economic growth, and this is something that we need to put into our heads. By combining hybrid technologies, AI-driven process optimization, and brine valorization, desalination plants can reduce energy costs, extract valuable minerals, and create a sustainable water economy. Water security starts with smart brine management, and the time to act is now. Thank you, and I look later to your questions.
Thank you. Thank you, Christos Harisiadis, founder and principal consultant at Brine Consulting. Your presentation has made it clear that smarter brine management is essential for water security and also an opportunity for economic growth. From hybrid solutions for brine concentration to AI-driven process optimization and to brine valorization, the path forward is turning desalination into a circular economy model. That's very clear from your presentation. Now let's turn to our final speaker, Jesus Ribas, who will discuss high-efficiency motor solutions and their role in optimizing energy use in desalination.
Okay, thank you, Christina. Thank you for having me in this presentation. Let me share my screen. Let me know you can hear that. Okay, can you see the screen?
Yes.
Okay. Motors, water scarcity, and rising energy costs make that efficiency is a top priority now in desalination. That's why we are here to discuss about the latest innovations. But to put that into context, let me introduce a little bit, very briefly, our company. If we are going to talk about motors, let me introduce WEC. WEC is a Brazilian company founded in 1961. We started as a small electrical motor manufacturer, and now we are a global leader in industrial solutions. We operate in more than 100 countries. We are a key partner in energy efficiency solutions. Some figures is that we have more than 60 manufacturing plants all around the world. Our largest industrial facilities is 1 million square meters, which is not so easy. We produce more than 60,000 motors per day. And we invest a lot in R&D. We are more than 55,000 employees. So this is just to put into context our manufacturing capabilities. What are the desalination challenge now with talking about this, the energy? Desalination is one of the most energy intensive water treatment processes, much than wastewater or processed water treatment processes. And like my colleagues were saying before, the reverse osmosis plants consume in the operational cost. If you do this breakdown of the operating cost, 50%, 40 something, 50% are due to energy. And those main consumers are in the main line of the seawater RO process, the reverse osmosis process. I'm referring to this equipment like the high pressure pumps, booster pumps, low pressure pumps. So all this is the point where we have to focus on. Why we have to do that? What is the need of this energy efficiency? We have to reduce the energy consumption to reduce the operational cost of the desalination plants. And at the same time, by doing this, we are optimizing the carbon footprint. We are reducing the CO2 emissions. This is the reason, and also with the water scarcity, this is the reason why governments and entities are so focused in looking for sustainable and cost-effective solutions. So what we can propose to achieve this with electrical and electronic components. We should be focused on the motors, high efficiency motors, no matter if these are low voltage motors with efficiency categories from IE3 to IE6. And also we propose the high voltage motor for large size desalination plants. These high efficiency, high voltage motors are made to measure. So this is important to consider that we have to design for a specific purpose and for specific operating points. And with this, we have to follow this with control and with the medium voltage drives, the process control, the smart sensors. So this is a whole system. So I imagine you can determine here, you can see here the many different areas of the seawater desalination plant. There are some areas, some processes, sub-processes that we have to consider. So everywhere you see a motor or a pump or a traveling band screen or whatever, there's a motor, there's a electrical cabinet, so we can force to do this energy optimization in these motors. But coming to the main processes that are influencing more the cost, we were talking about the intake pumps. The seawater intake is, they move a lot of water, big volumes, so they require a lot of energy. Pretreatment is key for the quality of the process, but you have there media filtration, cartridge filtration, DAF, or microfiltration, whatever this process, they are also furnished with motors and drives. And the most important is here, the water treatment process is based on the RO process, the membrane. So the high pressure pump, the low pressure pump, the booster pump, all these main line, all these components, all the pumps in these main processes, including the RID, they are responsible of the main part of the energy consumed by the desalination process. In this table below, this is an example of the motors we can provide to one. This is an example of 500,000 cubic meters per day. So this is just to give you a rough idea. So at the end, we have to consider the product application. Mainly this is low voltage motors, high efficiency motors, even permanent magnet motors. And for larger scale desalination plants, we are considering the high voltage motors and the VFDs, the frequency drives or variable speed drives. These are the products, and this is the idea of the configuration for higher efficiency solutions. As I told you before, low voltage motor from IE3 to even IE6 efficiency levels. High voltage motors with custom configuration maximize the efficiency and minimize the specific energy consumption for the desalination plant. To get this in the figures, 3 kilowatts hour per cubic meter, something like that. And with this idea in mind, we have to focus on different kind of motors all around the desalination plant. Low voltage motors, high voltage motors, permanent magnet motors, new generation motors that I will talk a little bit at the end of this presentation. For then, we have to continue studying the cooling systems, which is also important to improve the efficiency, and to optimize the control of the plant to avoid wasting energy, reducing the necessary power consumption. We have the drives, we have the variable speed drives or frequency drives, monitoring the plant with sensors that can help us to minimize the downtime and increasing to have a predictive maintenance to reduce the stops in the plant. And also all this can be integrated with renewables energies. Okay, so with that, I'm showing here 2 examples of desalination plants. A small one with, even in these small plants, desalination plants, with the use of low voltage motors like W22 models. In this project in Mantoverde in Chile, we reduce a lot the energy consumption in the intake chamber, in the seawater intake. At the same time, by reducing the intake, we reduce the CO2 emission, which was very important at that time for the client. And this is an example of a big, large-scale desalination plant. This is Ravik 3, 600,000 cubic meters per day. Now it has been running for some years, so this is very reliable, very, very profitable. And how we work on that? We were supplying the high efficiency motors for the main line and the medium voltage drives. So we enhanced the operational efficiency of this large scale desalination plant. And it's very reliable, very energy efficiency solutions assure the long-term sustainability of these plants. And maybe because of that, or because our success in this plant, we were awarded with Ravik 4 last year. How can we do that? We have to start from the very best beginning of the design. We have to support the designers, the engineering firms, the EPCs. The EPCs always worry about the correction curves, looking for the salinity, the temperature of the water. So they have to maintain the specific energy consumption. But with our motors and drives in the main process line, we can influence by having better efficiency in the components and reducing this SEC, the specific energy consumption. That's clear, but when we start to consider the electrical engineering of project of this desalination, we have to consider many aspects in order to get off to a good start. For instance, we have to pay attention to the type of motors, the starting methods, the current state of design in the market. We have to look for the economical aspects as well, because at the end this has to be a balance. Cooling methods, supply voltages, if we need any special test to validate the system. So this is quite important to make this balance and to have special designs consider all the aspects that may impact in the cost and the efficiency of the plant, because at the end it's a balance. So going into more details, but not so deep, because this is not a technical session. Our engineers have to define the motor that they have to design in order to achieve the best efficiency so that the product is economically viable. Okay, so and they have to configure the project of the motor made to measure for each desalination plant. So we have a motor configuration project for every opportunity. If we are going to talk about increasing the efficiency, we have to pay attention to the losses. So that's clear. The losses, we have to minimize the losses, and we have to balance mechanical and electrical losses. Because this is a balance between losses, considering the frequency of the motor, the number of poles, so everything has to be considered. Talking about the electrical losses, the Joule losses, there are so many tricky points that we have to consider. So the project is not so easy to do. It's not just taking a motor from the shelf. We have to consider the slot format, even the copper wire diameter of the winding, the air gap, the film effect, even for the iron losses in the core losses, the stator and rotor materials. We have to look for materials with the grind orientation, this impact to the magnetic flux, which is important. So higher cost, less heat, more expensive, but we have to consider all aspects and balance the motor like as a whole. For sure, we have to consider the mechanical losses as well. Is the friction due to the ventilation, the bearings, the heat exchanger. So this is important. And for sure, we have to follow the normative, the standards, the margin we have to follow in the specifications and in the regulations as well. And the same for the and the same for the drives, the medium voltage drives. This is mandatory to consider that there's all going to be always a medium voltage drive to drive this energy to the motor. And we have to consider in the electrical design of the whole plant, the supply input and output voltages, the ambient condition where these drives are going to be located, the wiring distance between the drive and the motor. This is normally a big issue. This is not normally a big issue in the desalination plants because the distance is not so long, less than 500 meters. So maybe we don't have to put any filter or something like that, but in some cases could be. The topologies, we have two topologies in the market, depending on the IGBTs. In the inverter, these small components in the micro power electronics in the inverter are made in low voltage or medium voltage. For sure, we have to look to the water system, the cooling system, air cool, water cool, or even a hybrid system that we are developing now. And also the drives have the motors, have the transformers, with different materials, you have different efficiency. But the most important thing about this configuration is to look at the whole electrical schematic configuration. With the medium voltage switchgears that feed the drive, and in turn, this turn the motor. By looking at these voltages, powers, we can optimize the investment prices and efficiencies of each of these components, so that together they can give the highest efficiency at the best possible cost. So by doing this, we can optimize the energy consumption. For instance, in one desalination plant, similar to the Rabbit 3 or Jubail or these ones, for a 600,000 cubic meters per day, for instance, just by increasing the efficiency 0.5 points efficiency in the high pressure pump motor, we are saving 4 gigawatts. That was 4 gigawatts only by these main pumps motors. 4 gigawatts per year is a lot of saving. If you translate this into carbon footprint, this is the equivalent to 1,000 tons of CO2 equivalent. This is not so a small figure. Okay, and we did that with the motors. We can do that the same for the drives. In this example, for a bigger plant, we were saving up to 8 gigawatts per year. That can be avoided if we are increasing the efficiency of the drives just a little bit, one point. So at the end, the final conclusion is that what are the benefits of improving the efficiency in the motors, in the main line or in the whole plant? That's clear. Cost savings and energy efficiency. We can reduce the energy consumption up to 30%. We have I5 motors, high voltage motors made to measure, fit to purpose. And we, in the same way, we are reducing the operational cost because we are reducing the electricity demand. At the same time, we are also using drives to optimize the process, to optimize the operating points, and we can automate the plant. So these energy savings links are linked directly to the reduction of CO2 emissions. So the carbon footprint is much less in the desalination plant. And this helps us to meet our targets about sustainability and to have more sustainable plants that can even be furnished with solar and wind turbines with more renewable energy sources. But for sure, our equipment has to be robust, has to be durable, has to be very reliable. We can reduce the efficiency, the maintenance costs. We can make tailored solutions to specific needs, and we are continuing evolving and developing new products. Just to finish, this is the final conclusion, but just to finish, let me show you one picture. Let me show you this disc. This is an axial flux motor. Okay, maybe this is the future. Let's see. This is an induction motor, the same power rating of this induction motor is this motor, axial flux motor, but is around 30 times smaller. So the footprint is incredible. With the same capacity, and we have a wide range of this axial flux motor that could be implemented, why not, in the desalination plants. We launched this axial flux motor technology, W80 axial generation. Maybe you can see that in some application in desalination or in other water treatment plants, but maybe this is the future. Let's see. So we are here to improve, to develop more products and increase efficiency that provide us more sustainable water on desalination treatment plants. So that's all from my side. Thank you very much for the attention. You have my email here. Just feel free to contact us anyway, anytime. So that's all from my side. Thank you very much.
Cristina, you are on mute.
Cristina, cannot hear you.
Thank you. Thank you, Jesus Rivas, Water and Wastewater Global Manager at WEG. We have seen the applications of high-efficiency motors, variable speed drives, and digital automation in desalination processes. Thank you for that detailed presentation. Then we have seen how we can improve plant performance and minimize unnecessary energy consumption. And of course, this translates into cost savings and long-term reliability, as we have seen in the examples in Chile and Saudi Arabia. With Jesus, we conclude our speaker presentations. And now we turn to our Q&A session, where our panelists will address your questions and further explore today's topics. So now it's your turn to join in the conversation. Please send your questions using the Q&A module at the bottom of the Zoom window, and please include your name and organization when you ask your question. This is a great opportunity to engage with our speakers directly. And we already have quite a few of those questions that came in, so we're going to start right away. And we'll start with a question from Lou Ingber from InPipe Energy in the United States. And the question is, how feasible is energy recovery in desalination? And what types of energy recovery technologies are most commonly used? And I throw it there for any one of our panelists that might want to answer that or try to answer that.
I will begin. How feasible is a reality from the 80s in all desalination plants that are implemented energy recovery devices taking advantage of the high pressure of the brine. The pressure of the brine is basically the same pressure that the inlet less the pressure drop in the membranes, which means it's a high pressure with a very high volume, which allows to recover the energy. From the beginning of the history of the energy recovery devices, there have been different things. For example, turbines coupled to the excess of the pump. More recently, there are the isobaric the isobaric cameras or interchange pressure exchangers, interchanging pressure between seawater and brine. In the case of those new energy recovery devices, it has another advantage. It's like the high pressure pump is more or less is half of the size of the previous high pressure pump, which means that we have reduced a lot the energy consumption of the plants until the current 2.53 kilowatts hour per cubic meter. There are many manufacturers doing this. You have the energy recovery from the United States. You have I don't want to forget anyone because it would be a problem. You have Calder-Weir. You have devices from Danfoss. There are many companies producing different devices with the same purpose, which is to recover the energy which is present in the bright discharge. Not sure if any of you want to add something, my colleagues.
Anybody else wants to add anything?
That's clear,
Yes,
Domingo. That's clear, Domingo. Is the energy recovery devices are very well known in this desalination plant, especially when we are talking about big plants. I remember the DUIR, the Saltec, all these processes, but commercially you can talk about few of them. Isobaric chambers are the most common use, and the reason is that we divert water one to the main pump, to the main high pressure pump, and then you divert some kind of water to the energy recovery device. So you are you are reducing the water to the high pressure pump, so the high pressure pump is smaller. So we are saving money, we are saving flow. So this is very important and it's very common use. But I don't know if the answer was coming from, was trying to talk about this in small industrial plants. For those industrial plants, maybe this is not so used. They are getting Danfoss, ERI, they are working on that. Fedco, all these companies work on the industrial sides. Industrial plants are also considering this energy recovery device, and this is a must. 20 years ago, we are not using that. We were using 30 years ago the Pelton turbines, right? But now it's mandatory. We have to optimize the energy consumption. So this is a must now.
Yeah, I think that the key of feasibility is, for example, for a seawater plant is mandatory, it's always. Yeah. But for a brackish water plant, it depends on the pressure and the flow. If you have a big flow with reasonable pressure to recover, is feasible, and there are some devices applied to brackish water treatment plants.
Thank you. Anybody else wants to add anything to that? We're okay with that. Well, thank you very much. We have a broad question about asking about the advantages and disadvantages of desalination versus, for example, advanced water reuse. Any takers for that question?
Okay. Domingo, do you want to start as water positive member, or you would like me to?
No, you want to begin? I will add some ideas after you. Thank you.
So I believe there are 3 pylons for the future of water. That is improved water management, water reuse, and desalination comes last. Yeah, you have to, and there are plenty of arguments going on in conversations going on in LinkedIn, for example, on that topic. Like it's if you keep putting new water into a pocket that already leaks, what's the point of that? And first we need to properly use what we have, and then move on to producing new water, or at least trying to do these things in parallel. That's my take on it. Domingo, what do you think?
Yes, I think the same. I think that we should put our efforts, first of all, being more efficient, not to lose water in our networks. It's crazy. After it, reuse as much as possible, and after it, desalination. I think there is another thing to consider, that reclaimed water is limited. You have a wastewater treatment plant at limited volume, and then you can reuse only the water you have. But and if you are limited and you need more water, then you have to implement desalinated water. On the other hand, of course, with the technical challenges we face currently with new pollutants or composed of emerging concern, microplastics, etc., the implementation of membranes is increasingly popular in potable water or in wastewater. And then the cost of this advanced water reuse is being closer to the seawater desalination. And then there are those kind of aspects you should consider it when you are thinking about a project.
I just wanted to add that I'm a big fan of the water reuse, and I think it's one of the solutions in the near future. But today, what we have is the technology to solve the water reuse is there. So, but what we have today is desalination plants, and as you said, when we are talking about adding resources or adding water to the water network to the use is desalination the way we need to treat this. No doubt that water reuse will have to have a big part of the cake once, probably not the technological, but some psychological constraints that are that can be in the table we will be able to overlap that.
It's not only about drinking water, right? It's about processed water. And it's mandatory, I guess, at this day and age, that the big industries reuse whatever water they can, starting, for example, with agriculture. Yeah, better water management, and try to save water where you can.
Yes, that's clear, Christos, but we have to have more reliable water treatment plants, reuse water treatment plants. We have to manage the process, have more reliable plants. That's clear. But what happens when there is not so conventional water resources? So we need more water. So we have to use desalination. It's not so expensive. We have to use that. So we have to increase desalination plants. So this is a lack of water. So it's water scarcity, and water stress is when you cannot manage this water, but you have to manage this, be able to manage this water. But when there's a lack, water scarcity, you have to provide more water treatment plants, and desalination is a solution. So both can be promoted at the same time, in my opinion.
Oh, yeah, definitely.
Okay, thank you all for this interesting discussion. So, of course, we start with improving the efficiency of our networks to manage better the water that we already have in our networks, but then we have a lot of room for desalination and a lot of room for reuse. Those two will be a big portion of the solutions that we're going to have in the future. So we're going to look now at a more specific question that comes from Amel Georgsdottir. He's a senior project manager at the Geothermal Research Cluster in Iceland. And the question is, how do you foresee the application of geothermal energy in desalination projects? I don't know if any of you could answer to this. Because
that's a difficult question. Of course, you can use it for producing energy, but for increasing, for example, if you have heat, of course, it will be useful for evaporation. For example, for a reverse osmosis plant, if you increase the temperature, you can produce, you have more permeability on the membrane, you produce more water at reduced pressure, but we should study the economical feasibility of the investment and the time for recovering this investment. I don't have the experience of direct coupling of geothermal energy with desalination, but of course, I think it's promising, and probably there will be places where it will be economically feasible.
Thank you. Yes, so a promising option in those regions of the world where it's available. So we'll go into a few questions on the energy efficiency and optimization of processes in the plants. And there's a question from Osama Sengaf, operation manager at Metito in Saudi Arabia. And the question is, how can efficiency in desalination processes be improved from high-level system design to cutting-edge energy-saving equipment? So I think there are lots of things that you may want to mention here.
Well, I don't know. This is a very general question. So What I will say is that we have to start from the beginning. During these 20, 40 years, we have designed the plants, we have constructed the engineering firms, designing the desalination plants just to minimize costs, construction costs. This is important, but now we are in the area of optimizing the energy consumption. So maybe just from the beginning, we could be looking for more, I would say, more efficient concept, more efficient components, subsystem processes. For instance, not only the membranes, but energy recovery devices, components, instrumentation, everything designed from the perspective of minimizing the energy consumption. So if we consider that, and the engineering firms relocate their ideas, not to have not paying so much attention to the civil construction because of the moving earths or of the piping diameters, and we reduce these hydraulic losses, we reduce the energy consumed by the membrane or the pressure drop in a valve or wherever you can imagine, or even in the motors. I don't know, moving that to my side, but if we study different alternatives, breaking edge technologies or process or components, maybe we can slightly define a new designs in desalination plants. So not only focus on big construction. This is economy of scale for sure, but for industrial plants, brackish and seawater plants, this could be also considered as an option, or in the design, I mean. I don't know what do you think?
Yeah, I agree. I will add, coming back to the communication thing, that the desalination industry, I think, is the industry with the more spotlight in our energy consumption more than any other more consuming energies, and we have reduced our energy consumption by 10 in the last years, and we are close to our thermodynamic limit, and then we are trying to reduce 0.1 kilowatts hour per cubic meter or something crazy like that. We have reduced it by 10, and even with those kind of things, we are always in the spotlight. It's very energy consumer, etc. It's curious.
Yeah, that's true.
But I think we are in the right way, and as you say, and now from the beginning of the projects, we are very concerned about the energy consumption. We have to guarantee an energy consumption, and we have penalties if we don't meet the standards required and these kind of things. And of course, all the industry is also involved in the decarbonization process. That means that is one of the main focus. Energy and environment are the main focus of the design of the new plants, of course.
Thank you. We have a question that's kind of related to what you have been discussing. So would the desalination plants be more efficient if the EPC contractor were required to operate and maintain them for a minimum of 5 years? What do you think?
No, I don't think so. We are we are EPC contractors, and we are usually also on the O&M contract, on the O&M operation, and so I guess Domingo has a very right point. We are on the spotlight on the consumption all the time. We want every year to reduce another 5%, 10% on the consumption per cubic meter. I think we saw the table that Domingo showed us with the prices of the cubic meter. Cubic meter is 1,000 liters, so it's 0.7, 0.6, 0.5. We want almost for free, right? So and that include the energy cost. So the EPC and the O&M operator wants to have the minimum consumption, and it's true that even once you finish with the EPC, after that the O&M is able usually to reduce even more the consumption, because on the EPC test you test it with the full capacity of the plant or everything on and everything working, and then the operator comes and make their magic to reduce depending on the quality of the water, depending on the but I don't think that it will make big changes to keep the EPC on the equation for 5 years. We stay on the equation, yeah.
I think that a good point is that globally the most common kind of contract in big desal plants for governments is a concession, is a PPP project with for 20-25 years, where the SPV includes the EPC contractor and the O&M company that in general they are the same company or related. No? And this is very good because if not, maybe the objectives of one company only constructing will be different of the objectives of a company thinking in operating at the plant during 20 years. Anyway, there are penalties if you don't feed the required energy consumption, and then this can be another point.
Okay, thank you.
Curiously, in Spain is the exception where we don't have PPP projects for desalination.
Mm-hmm.
And maybe this is because the EPCs here in Spain have a lot of experience. And when we operate the plants, we construct the plants here, we are thinking about the operational costs, and we design for have a very reliable plants. So maybe the question at the beginning was thinking about, okay, what about if the EPC constructor finish the construction, they have a test, a final test, 24-hour test or whatever, and they leave the plant. Could be leaving a reliable or not reliable plant? Yes, that is the question. But at the end, we have to operate the plants, not only for optimizing the energy consumption to the operation phase, but at the end, even an EPC is very well inspected to see that they are getting the best results in reliability of the plant, performance of the plant, and even energy consumption optimization. So at the end, we are going to BOT contracts, EPC contracts. For me, it's the same because everybody is looking for the operational costs, operating costs, and energy reduction during the operational phase. So it's mandatory now to be thinking in the operational costs, energy service during the whole life of the plant. So here in Spain, we are not doing that because we are thinking on that. So this is easy. This is easy. This is now in our DNA.
Thank you. Thank you all. We have another question looking a little bit more closely at costs, since we're talking about costs, and it's from Laura Blasco, Technology and Transfer Lead at Centrion Pharmaceuticals in Spain. Do you foresee an increase in costs, OPEX and CAPEX, due to new quality requirements in drinking water, such as PFAS regulations?
No, we can't expect an increase of price of desalinated water in this case, because you know that the process we are using is reverse osmosis, which is rejecting most of those components. For example, if we are speaking about reclaimed water, probably we will need other previous things like an advanced oxidation or whatever, or maybe small molecules can pass through the arrow, but in general, the arrow rejects all kind of pollutants, and we should not need additional treatment for fitting these new requirements from the European Union and other countries in speaking about components of emerging concern of even microplastics.
Okay, thank you, Domingo. Anybody want to add anything to that? Okay, so let's move on because we still have quite a few questions. And we have a specific one about motors. So I guess that would be for Jesus. And it's from Miguel Dominguez, Global Area Manager at Innomotics Motors and Drives in Spain. You mentioned IE6 motors with better efficiencies. Is there already an established standard or norm for IE6 International Efficiency Class 6 motors?
Yes. Thank you for the question from Innomotics. We have the W23 Sync Plus. It's a hybrid motor. We can achieve very easily the IE6 standard. And even in our definition, I can imagine our competitors can do the same. We can even go to up to IE8, but it's not commercially available nowadays. But this IE5 we are offering very frequently, and the IE6 is launched time ago. We call this in our model is W23 Sync Plus, which is a new standard, a new model, complies with this high efficiency. We have the wider range of powers for these low voltage motors. So this is part of our R&D department who develop more products. So we are very happy because the products we sell every year came from the products that has been developed in the previous 5 years. So this is one of these examples. The axial flux motor is the same. So yes, we have this IEC standard. We comply with this.
Thank you, Jesus. We move on now to a question about membranes and pretreatment. And this is from Ashish Wade, Business Development Head for MENA at Ion Exchange India in the United Arab Emirates. How do new materials, such as hybrid membranes or nanomaterials, enhance the efficiency and lifespan of desalination membranes? Would anybody want to try to answer that?
Okay, as I was mentioning, there are new technologies and new things, new materials. We are speaking about new spacers or ultrafiltration membranes with ceramics or other materials in order to reduce energy consumption or increase permeability or productivity. Those kind of things are good from the point of view of efficiency. We can increase, but the problem is that I mentioned before, we have the thermodynamic limit and we only can increase a little bit the efficiency or to reduce in very reduces steps the energy consumption. Of course, those kind of measures are good. From the point of view, you have a very good pretreatment, avoiding membrane fouling. You will have less shutdowns of the plant. You will reduce, you increase the productivity, which means also the specific energy consumption will be lower, and then all these kind of things or materials are advances that are very welcome for the technology, but unfortunately not for revolutioning the energy consumption or reducing, because we have a very reduced margin for it.
Thank you, Domingo, for that. We're going to take one last questions. There's quite a few ones, but since we've already been 90 minutes with the session, we want to look at the future, and we have the perfect question for this. It's from Marco Pitacco, Business Development Manager at Fisia Italimpianti in Italy. And the question is asking about major future disruptive breakthroughs or events that you foresee in the next 5 years in this area. If you would like to try to speak to that.
I don't see major breakthroughs or disruptive events that change. It's true that in the asymptotic of reducing and make things more efficiency, that makes reducing the consumption. That will continue to develop. The use of recovery of brine or minerals and things like the ones that Christos showed us, I think that's another important develop, but not a breakthrough. And in terms of energy, I think that the real breakthrough will be able to couple, as I said during my presentation, to couple solution in which renewables and onshore, offshore, and diesel plants are linked completely together and being able to work almost together. That will be major breakthroughs.
I have the same opinion in speaking about processes. We can expect something revolutionary, but maybe we can speak about something that is revolutionary all our society, which is the artificial intelligence. Maybe the plants of the future will be operated by robots or by an artificial intelligence, which is happening more or less. Maybe it will be more efficient than the current system of operation, etc. But the digital transformation is transforming all the industry and the society. But at this point, we can say that it's disruptive because it's here now. No? It's not the future; it's the present.
Yeah, that's true. I don't see any breakthrough technology either. What I could imagine is having innovative engagement between different processes. I mean, the pretreatment linked to the process treatment and the post-treated water pumping station, and having energy recovery systems to recover the energy from the plant, reuse internally the water treatment. So, and a summary, a bunch of technology or process integrated within the desalination plant, optimizing the intermediate stages, eliminating pumping station, eliminating reservoirs. So optimizing the processes, sharpening the pencil to optimize the use of components could be the potential. But nowadays, the RO membranes, we can have ceramic membranes, we can have the actual membranes. This is the core. I don't see any breakthrough technology, but we can increase in few years this kind of integrated process related to energy. Maybe this helps, but as my colleague said, I don't see any breakthrough technology that can eliminate the RO membranes nowadays.
No, definitely not. I have to agree with Jesus and with the rest of the presenters here. First of all, energy-wise, there is no clear innovation that can become a breakthrough. Process-wise, Miguel also mentioned the brine. Yeah, as far as I'm concerned, we already have breakthrough technologies that can be applied in commercial big scale. And perhaps we should look more in potential business cases where they make sense. A breakthrough might be, as far as I'm concerned, in our way of thinking, where we can find new water sources. And as far as I'm concerned also, even if we build the desalination plants that need to be built, we will still need more water, and we will need new water sources to couple with desalination. And we see craze in the last couple of years with new options. One of them is AWG. Recently, atmospheric water generation. Recently, we had a company in the US gaining 100 million investments. Yeah, quite big. We had a big fight in the GWI posts. Yeah, recently in LinkedIn about this. Again, we have to be innovative in order to find the water we need.
Okay, thank you. Thank you, all of you. Yes, we're going to have to use the water we have, and we expect innovations in integrating processes, but no major technology breakthroughs. But we can certainly improve efficiency in those processes. In the interest of time, we're going to bring the webinar to a close. I would like to thank you, our speakers. Domingo Zarzo, President of AEDIR and Innovation and Strategic Projects Manager at Sacyr Water.
Thank you very much.
Miguel Aritio, Director of Energy Resources and Business Development for North Africa at Acciona. Christos Harisiaris, Founder and Principal Consultant at Brine Consulting. And Jesus Rivas, Water and Wastewater Global Manager at WEC, for sharing your insights with us today. Do you have any final remarks you would like to share?
For me, the main challenge of desalination, communication.
Communication and education. That's right, Domingo. I agree with you.
And information dissemination, collaboration.
Yeah.
Perfect.
Okay,
Well,
thank you.
Miguel?
No, I was saying thank you very much, Cristina.
Thank you.
Well, thank you all. And yes, communication and information dissemination, it's what we're trying to do, and we'll keep on trying to do that. Thank you all. And thank you to our audience for joining us today. And we remind you that you can download a certificate of attendance by scanning the QR code that will be displayed on your screen. And today's session has emphasized the importance of energy efficiency in desalination as the industry works to balance energy use with the challenges of water scarcity. We've seen how there are innovative energy-saving technologies that include integrating renewables, smarter brine management, and others. Our experts have shared the strategies to improve the sustainability of operations and with useful perspectives on making desalination more efficient and environmentally responsible moving forward. Just a quick reminder before we close that the webinar will be available for on-demand viewing on the website of Smart Water Magazine. And also key insights from today's discussion will be featured in the upcoming issue of Smart Water Magazine print edition, which will be released in March at the end of this month. That will ensure that the knowledge that has been shared here will reach a global audience and has a lasting impact. Thank you very much for being with us today.